Hi budding engineers, welcome to Section Engineering Lectures and welcome to the new playlist on the design of steel structures as per the limit state method IS 800-2007. In today's class we shall see the analysis and design of steel roof trusses, wherein we will try to see the design of top chord member as well as this bottom chord member. The top chord member is sometimes called the roof rafter or principal rafter, and that is a prime compression member, and the bottom chord is sometimes called the main tie. In the previous class we have seen the analysis of this roof truss subjected to dead load, live load and wind loads. We have calculated them as well as we have done the analysis as per the method of joints as well as method of sections, right? I hope you enjoyed the discussions there, and if you have really enjoyed, then don't forget to click like, share, subscribe to our YouTube channel. Now before we see the actual discussion, let us see the brief profile of the speaker. That is Dr. D. Rupesh Kumar, obtained my BTech in Civil Engineering from Nagarjuna University in 1994, MTech Section Engineering from JNTU Hyderabad in 2000, and PhD Section Engineering from JNTU Hyderabad in 2009. Presently, I am working as Professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete design, steel structural design, structural analysis, fundament analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers in international as well as national journals and conferences, organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 3 books, supervising 14 PhD scholars and supervising 30 ME theses. I am actively involved in various consultancy works that are offered by the department and completed over 770 design proof checks and 150 plus designs of the reinforced concrete designs, steel, composite, low-rise, high-rise, multi-story buildings and road as well as rail bridges. Now, that is how once we examine, let us see what we will be discussing in today's class, right? In the previous class, we have seen this analysis of the Fink truss. A Fink truss was given where we have fixed the geometry, we obtained the lengths of each of these member, and we have obtained the dead loads as well as the live loads, and we obtained the live wind loads, and we did the analysis by method of joints. I have just done one method of one joint only, A, that I have shown. Likewise, we have obtained the design forces. In today's class, we shall see the designs of these different members, right? However, in today's class, we shall see the design of the top chord member, this top chord member, as well as the bottom chord member only, right? Bottom chord member only, right? Now, let us move to the discussions. In the previous class, you have seen the wind. Particularly, let me go to the wind loads, right? That is as per IS 800. As per IS 875 Part 3 Old Code 1987, wherein we would have this value of the design wind speed Vz is equal to Vb K1 K2 K3, right, that we have obtained as 41.83 meter per second, whereas as per the new code, let me show that new code at a quicker pace, right? This is right, Vz is equal to this new code is IS 875 Part 3 2015, right? This is Vz is equal to Vb K1 K2 K3 K4, where K4 is the importance factor for cyclonic regions only. However, in the previous class I have even included K4 assuming it to be a cyclonic zone. However, our Allahabad is not there in a cyclonic zone, therefore K4 is equal to 1. K4 is equal to 1. Therefore, in such a case, now that Vz is equal to 47 is the basic wind speed multiplied by K1 is 1, K2 is 0.922, K3 is 1 and K4 is 1 because it is not the cyclonic zone. Therefore, now Vz will work out 43.33 meter per second, whereas here as per the new code IS 875 Part 3 class 7.2 page number 9, this now I do have, right, PD, right, PD is given by 0.6 Vz square, wherein that Vz itself now that PD is now that Pz multiplied by Kd, Ka, Kc. Therefore, that also we have explained the other day. Therefore, it now works out. Say PZ is equal to 1.1267 and KD is equal to, because if I substitute now into that 0.6 multiplied by 0.6 multiplied by 43.33 whole square, it works out 1.1267 kilometer per square meters, and KD is 0.9, K is equal to 1, KC is equal to 0.9. Therefore, my design pressure PD is equal to 1.267 multiplied by 0.9 multiplied by 1 multiplied by 0.9. It works out as 0.913 kilometer per meter square only. However, as per the old code, means IS 75 Part 3 1987, we obtained PD as 1.05. However, already showed how to analyze this using this 1.05 kilometer per meter square, whereas as per the new code, now I'm just getting a value less than this, which is 0.913. Therefore, I am on the safe side. Therefore, now I'll proceed with the designs. Now, before I go to the design, let me see the summary of the analysis what we did the other day. Right? This is how the entire half of the symmetry of this truss I am showing that the top chord member and bottom chord member. This is the main sling, this is the minor sling, and these are the struts which are analyzed the other day, right? These are the design forces. Right? I am just recalling that these are the design forces that in the rafter, means top chord member, right? Even I have shown B1, right? That this value obtained as minus 58. That minus indicates the compression force. Minus indicates the compression force, right? Even due to dead loads, we have analyzed and we obtained that as minus 52.5 in the at the joint, right? B1 or that member was L0U1, right? And even for the wind also I have done analysis for the three cases, right? When theta is equal to 0, right? And when theta is equal to 90 degree with two types of coefficients, right? That is how I obtained the results out of these two, whichever is maximum. Therefore 111.6 when theta is equal to 90 degrees governing, and when theta is equal to 0, right? And plus 95.6. Here plus indicates tension and minus indicates compression, right? That is how I got the analysis results as compression tension due to dead load, live load, wind load, theta is equal to 0, theta is equal to 90 degree. Like that, even I have summed up all the results the other day, hence I am just recalling this, right? Now I'll do for my design, what now I'll do is now I'll take all the load combinations 1.5 multiplied by dead load plus live load. Therefore, now if I multiply 1.5 multiplied by 158 plus 52.5, now I'll get that result as minus 165.75, right? Similarly, now I'll take this dead load plus live load plus wind, right? Left, right, whereas now I'll get right. Even I'll do this as well as in other case I'll do with plus 111.6. Therefore, now this will govern the result. Plus 11.6 minus 52.5 minus 58. That multiplied by 1.2, if I do, now I'll get that result as minus 17.88. Similarly, 1.5 multiplied by dead load plus wind load. Now I'll take this wind load 111.6 plus dead load minus 58 that multiplied by 1.5. Now I'll get say plus 80.4 like that. If I see in the other members, I'm getting these are the different combination forces in the top chord member. Out of all these results, now you can see that direct minus result is maximum only in the L0 U1 as well as even at the end U7 L5 also it is the maximum. Therefore, I'm just recalling that as my final design compression force, as it is already factored minus I'm not putting now, I'm saying compression force of 165.7. even now we'll see where I'm getting the maximum plus value. Therefore, now you can see that maximum plus value is encountered in this U3 U7, sorry, U3 U4, I'm sorry, right? That plus indicates a tension. Therefore, I would have the design tension as 95.4 kilonewton as the design forces in the rafter or top chord member. Similarly, even I have shown the other day, right? The main tie. In that main tie, I am getting for dead load 52 compression, and due to live load 47 compression. Whereas due to the wind I got tension as minus 76 when theta is equal to 0 and minus 102.4 in L0 L1 member. Similarly in other members you can see the other results, but now if I do these combinations, 1.5 dead load, live load, 1.2 multiplied by dead load, live load, wind load, 1.5 multiplied by dead load, wind load combinations, I am getting the first result in this L0 L1 as compression, design compression as 148.5 kilonewton, kilonewton, right? There is a compression, student, right? Compression, whereas even now you can see that it is also subjected to same amount of tension, right? Therefore basically the main tie is a principal tie. Therefore now I'll take out of all this 1.5 dead load, live load, because this being a main tie, therefore it is subjected to the tension force of 148.5 almost. Even it is subjected to a compression of 148.5. However, this being a main tie, because bottom chord member is a main tie, I'll recall this as my design force as the tension force. I will not design for tension and I'll check for compression, right? Therefore now I'll design for tension and later on I'll check for the compression. Therefore now I'll see where I'm getting minus value, maximum value. Therefore I'm seeing that in the same L0 L1 I'm getting minus 75.6 is the design compression, right? That is how I got the design tension in the main tie or the bottom chord as 148.5, whereas the design compression as 75.6, right? Like that, even I'm getting the design forces in the strut, right, due to these combinations as plus 35.4. even now you can see, right, I do have this 35.4 as a design compression in the strut, as well as 37.8 here, right, as a design tension. Whereas similarly the minor sling I'm getting, right, maximum value as plus 19.95 as the tension force, plus indicates tension force, as well as I'm getting a maximum value of minus 22.5 as the tension, as a compression, right, in minor sling. Whereas in the main sling, I'm having a design force of, right, tension force of minus plus 58.05, because more than that I don't have any value, right? 39 is much less than this one. Therefore this is my design tension force. As well as in the negative values I can see that, right, minus 64.05 is a large value out of all this, right? Therefore there is my compression force in the this main sling, right? This is the main sling, this is the minor sling, this is the strut, right? These are the struts, and this is the top chord member and bottom chord member. Once I do this analysis, now what I'll do is, now I'll go for the designs. Let me initiate the design, student, right? Now I'm just recalling all these forces, and even we know what are the lengths, student, right? This analysis what I done the other day, I'm just reminding you, right? And so now I'll switch over to the designs, right? Now designs of the members and as well as the bolted connections, right? Now, however, what we are doing is that for the top chord member and as well as the bottom chord members, we are using two angles back to back. Even for the main sling also, right? Main sling also we are using two angles back to back like this, right? Two angles back to back to one side of a gusset plate, and it is also given the problem that use Fe410 grade steel. Therefore, for that now I do have ultimate stress of this steel. Fe is equal to 410 Newton per meter square, and yield stress is equal to 250 MPa Newton per meter square. And also from IS 800 2007 table 5 page 30. If I go to the page 30, now I do have the partial safety factors. Let me go to the page 30 student, replica page, right? And IS 800 page 30, right? Page 30 is this one, right? Therefore I do have the partial safety factors for the materials, right? If at all I do have the stresses governed by the yielding, gamma m0 is equal to 1.1, and if all the stresses are governed by the ultimate stresses 1.25, whereas even I'll be using the bolts like this, the bolts, right? Therefore for which generally we will be using the ordinary black bolts. Therefore they are governed by the friction. Therefore friction bolts gamma mb, we'll be using the ordinary black bolts, student. For the bolts in bearing, not friction, right? Therefore bolts in bearing type, therefore gamma mb, where and the partial safety factor for the bolts 1.25, right? Assuming them to be shop fabricated, even for field fabricated also 1.25, right? These are the different partial safety factors. Once I note down the partial safety factors, let me see the other data, right? Other data. This is how the data I just noted for this M20 20 mm diameter bolt I am assuming, right? 20 mm diameter bolt of grade 4.6. Therefore, the ultimate strength of this bolt is equal to 400 Newton per meter square, and the partial safety factor from this table just now we have seen that it is 1.25. And what is the net area of this bolt? As per this IS 1367 part 3 page number 2000 as per the 2002 code page number 9, and A and B is readily available as 245 mm square, right? You can directly visit that, or we can say it is approximately equal to 0.78 multiplied by the grass area 5/4 multiplied by 200 square. Both will be the same result. 245 is the net area, at the threaded section, at this threaded section, right? Then also I am assuming the gusset plate of 12 mm thick, right? This is my assumption. Therefore, the stress ratio epsilon is equal to square root of 250 by Fi, whereas Fi of the steel is already 250. Therefore, this stress ratio will now work out a unit value 1. Now, let me initiate the very first design as the design of rafter L0U4, this one. Let me go back to this figure related. This is that rafter, right? This is that rafter, right? Principal rafter, that is called the principal rafter, right? Now I'm designing this principal rafter using two angles back to back. Please make a note that this section consists of two angles back to back like this, right? Two angles back to back of a gusset plate. Right? Now, using the bolted connections, right? Now, however, just now we have concluded that the design compression, I am recalling that from that table, has 165.7 kilonewton, as well as the design tension has 95.4 kilonewton, right? From this table, just have recalled this result at 165.7 and 95.4 for this rafter or top chord member. Therefore, these are the design forces, and once I recall the design forces, even the other day we have found out the length of the member. Now what I'll do is I'll first, out of these two results, right, generally we'll always be designing for the compression and we'll making a check for the compression, because the design for compression is from the buckling point of view, whereas the tension, in such case it will not be buckling, right? Therefore, generally the members will be passing, if they are passing in compression criteria, right? Well, therefore, with that assumption, now I'll design for compression using these two angles back to back. That is my assumption, right? Even the length of this member, right? L0U4. Let me go back to this figure. L0U4, right? L0U4, right? This, right? Here to here. This is 2.235. We have obtained the other day. You please see, right? Therefore, now I'll say that I'm just recalling that data. Therefore, panel length 2.234, just now shown, and I'm assuming double angles provided on opposite sides of a gusset plate of 12 mm thick, as shown in this figure, right? Now, however, I need to obtain what should be the cross section, what should be the section, right? Now I'll obtain that, right? Therefore, now I'm designing for compression. Now what I'll do is, even if I go to this table 10 of IS 800 2007, page number 44, student, let me go to that page number 44 of IS 800, right? There is a page number 44. Right. However, these angles from this buckling class from table 4, we can see that these angles about any axis are C buckling class. You please see that, right? Channels angles, right? These belongs to C buckling class. Therefore, now what I'll do is from this, now I can say that, right? for this buckling class, right? Assuming slenderness ratio, because here the load almost 165 kN is there, right? Almost medium load is there, therefore I'm assuming slenderness ratio a medium value of lambda. Even because that length is not too large, 2.23, approximately 2.24 meter is not too large, therefore keeping in my past experience I'm assuming slenderness ratio lambda is equal to 100. Now from IS attended 2007 table 9C page number 42. Let me go to the page number 42, student, right? Page number 42, right? Therefore I am going back, right? Table 9C, because this is buckling class C. Table 9C is applicable. Design compressive stress FCD for column buckling class C. For column buckling class C, for Fy is equal to 250. For Fy is equal to 250, now we can see that FCD design compressive stress for lambda is equal to 100. It is 107. Therefore, once I note down that value, therefore now what I'll do is, now this is I've just noted that 107. Therefore, the cross sectional area required A Rick. Now I'll get that cross-sectional area required is equal to, say, a value, right? Say a value A required is equal to that design compression force. Design compression force is C, which is 165.75 kilonewton. 75 kilonewton, that divided by FCD 107. It works out, say, 1549 mm square. 1549 mm square. However, you increase this value by 25 to 50%, right? However, now let us say even if I increase this by 25%, 1549 multiplied by 1.25, therefore I am getting approximately 1936 mm square. Therefore, now from SP6 1967 table 22 page number 102. Now you try with a section having an area 1936. However, I want to optimize the section. Therefore I'll just simply proceed without any increment. However, as a student, you don't proceed with 1549, but you proceed with 1936 mm square. That section only you try to choose that section. However, I'm trying. Let me go to this SP61 page number 102. Yes, right. Yes, I'm there here, right? There, I'm there in this table 12, right? Where two angles back to back. Now what I'm doing, like I said, where I'm choosing ISA 65 by 45 by 8, because that section has 1634 mm square, 1634. But as a student, don't proceed with that. You just proceed with 1936. Therefore, as a first trial, as a student, what you can do is that you choose ISA 70 by 45 by 10 as a student, which furnishes 2104 mm square. That is okay for you. But however, I want to optimize the section, and now I'll try with ISA 65 by 45 by 8 furnishing 1634 mm square. If at all it is failing, then obviously there is no other option but to go for this ISA 70 by 45 by 10 furnishing 2104 mm square. Therefore, let us say I want to optimize the section. Let us see how it works out, right? Therefore, I am noting down that area 1634 mm square and the radius of variation about the major axis, right? About the major axis. Let me show that radius of variation about the major axis is not this one, right? Is seen, right? RXX as 2.02 centimeter or 20.02, whereas about minor axis means about YY axis, it is like this, right? Now let me show, right? Therefore it is about this minor axis, because I am using a gusset plate of 12 mm thick. However, the distance between these two angles is now 1 centimeter or 1.4 centimeter is only available. I do have 1.2 centimeter. Therefore, now what I'll do is I'll note down for 10 mm that RYY about y axis is equal to 21.1, and as well as 14 mm that RYY is equal to 22.8. Therefore, now I'll interpolate. interpolate. Therefore, that is our just noted down this table, student, right? You can see I'm interpolating. Therefore, the radius of variation about weak axis is equal to 22.8 minus 22.8 minus 21.1 divided by over 14 minus 10. 4 difference. However, I am calculating over a difference of 12 minus 10, 2 difference. Therefore, it works out say a value. Sorry. 14 minus 12 over a difference of 2, therefore it works out say value 21.95 mm. Therefore, out of these two, now you can see that right, still the RZZ is the minimum value compared to the top is RYY. Now you can see that because we have put the angles back to back of a gusset plate, obviously RYY is greater than that of the RXX about the major axis. This is the XX axis, this is the YY axis, or this is the ZZ axis as per the new code, right? Therefore, that will govern the design, right? That will govern the design. Now, next. However, if I go to this IS 800 2007, page number 35, class 724, right? Let me go to that page number 35, student, right? Page number 35. Page number 35 is like this, right? 35. Yes. Right. Now what I can see here that the effective length of compression members calculated from the actual length, right, should be center right. However, the effective length for compression members in trusses, this is 724, right? For bolted, riveted, welded trusses, braced frames, etc., the effective length KL of the compression member shall be taken as 0.7 to 1 times the distance between the center to center of the connections for the continuous members, right, depending on the degree of end restraint provided. Right, end restraint provided. Therefore, now I am assuming that it is 1 for if at all it is connected by means of 1 bolts, right? If at all it is connected by means of say 2 or more number of bolts, then partial fixity. However, minimum say 4 or more bolts means almost fixity, right? 4 or more bolts means fixity, right? Therefore, now I am assuming a partial fixity. Therefore, in between these two, therefore, or say factor K value as 0.85. Therefore, the effective length about that major axis, where this member is, this top part member is a continuous member, student. Let me show this, right, once again, right. This is a continuous over this panel, right. 1, 2, 3, 4 panel lengths are there. Therefore, it is a continuous member like this, continuous member, right. When the reflected profile will be like this, right. Reflected profile will be like this, a continuous reflected profile, right, like this. Therefore, because it is a continuous, I am assuming partial fixity as a 0.85 as a value. Therefore, LZ is equal to 0.85 multiplied by 2.235. It works out say 1.8997. Similarly, the effective length about the minor axis, YY axis, where about the minor axis, this member is discontinuous. Please see, it is discontinuous, right? Therefore, there for discontinuity, it is 1. Therefore, LY is equal to 1 means 2.235 or say 2235 mm. Therefore, the actual slenderness ratio lambda is equal to about the major axis is LZ by RZZ, which is 1899.7 divided by 20.2. It works out to 94.04. Similarly, the slenderness ratio about the minor axis LY by RYY is equal to 2235 divided by 21.95. It works out a value of 101.8. You please see that, right? Out of these 94.04 and 101, what governs is 101.82 about that minor axis, because of this one partial safety factor, this K value, it is now governed, assuming it to be almost right connected by means of only between these two panels only, which is like a discontinuous, though it is not discontinuous about y axis, it is discontinuous, right, like this, right? Therefore, now it will be designed only for 101, whereas in the initial assumption we assumed lambda is equal to 100. Therefore, our assumption is true. And also, if I go to this table 3 of IS 800 2007 from page number 20, student, let me go to that page number 20. Page number 20, I am going to that page number 20, say yes, right. Therefore, now I can see that for a member carrying compression loads resulting either from dead load and live loads, then 180. If at all it is subjected to, however, you please see that it is also the resulting forces are combination of the wind and live load, then it is 250. However, here we already considered even wind and live load, therefore the slenderness ratio should be less than 250 as per this table 3. Therefore this 101 is much less than 250. If at all is purely because of the dead load and live load, then it should be 180, right? Okay, it is less than 250 because even I do have the load combinations resulting from wind load also, therefore it is okay from that point of view, right? If it is not okay, then there is no other option but to increase this section from the assumed section to the next higher section, student, right? That is how we can contain, right? Now once I get this lambda is equal to 101, now once again I'll go to the same previous table what I have shown, table 9c, where I am noting down the for this slenderness ratio lambda is equal to 80, I do have FCD is equal to 107 just now shown. Similarly for 110 I do have 94.6. Therefore the design compressive stress is interpolated as 107 minus 107.94 minus 94.6 over a difference of 10. Therefore over a difference of 1.82 is how much? It works out say 104.7 Newton per mole square. However, in the initial assumptions we thought it to be 107. Almost we are there here and there, therefore my assumptions are correct. However, as a student you need to increase this area by at least 25 to 50% if you are failing in these, right? I have assumed 107, I got 104, therefore I am almost sharing their same. I have assumed slenderness ratio lambda is equal to 100, I reached 101, but you may not be reaching that accuracy of the results at the end. Therefore it is better always you increase this area by 25 to 50% as a student, right? Therefore now once I am designing this top part member, I am designing this part, right? Therefore now as per this IS 2007 table 2, even we know from page number 18, just now we have seen that stress ratio is equal to square root of 250 by Fy 251, and even from figure 19, let me go to that figure 19 of page 18, student, right? Figure 19 of page 18, let me go to that figure 19 of IS 800. Yes, figure 19 page, that page number is from page number 18. Let me go to the page number 18. Just bear for a moment, right? 18. Yes, 18. Now I am there in page number 20. Therefore I am going back to 18. Page number 18. Yes, therefore I do have here the definitions. What is B, what is D, they are given, right? And even they are shown here in picture also. What is B, what is D, you please see, right? Therefore from this figure 2 also, what is B, right, what is D, they are given. Therefore now I'll calculate these ratios. Therefore now it works out, say B is equal to 45, right? D is equal to, right, what is that B, you please see that, right, two angles are put back to back in such a fashion that the longer leg is connected to the side of one side of a gusset plate. Therefore the outstanding leg is called the width B is equal to 45, and this connected leg is 65, and the thickness is equal to 8. Therefore now I'll calculate what is the B by T ratio. It works out say 45 by 8, which is 5.625. It should be less than as per this table. Just now I've shown that table, right? Let me go back to this table, right? It should be less than 15.7, right? Now we can see, right? Therefore the outstanding leg of an angle, when it is with its back in continuous contact with the other components, yes, right? Even otherwise you can say outstanding leg of an angle in contact back to back in a double angle member, right? Therefore now I have double angle member. Therefore if it is less than 15.7 epsilon, then that is semi-compact, right? Otherwise Otherwise, if it is more than that, then it is a slender. However, now I got this result as less than 15.7. Even now we can see that, right, as per this even this 5.6 is, right, less than 9.4 epsilon, means this is plastic section, class 1 plastic section only, as per this 9.4 epsilon. Therefore this is plastic class 1 section. However, now let me also check along the depth direction, right? Along the depth direction also, d by t is equal to 65 by 8. It works out, say, 8.125. 8.125 is much less than, once again, this first 9.4. Therefore, even the depth is also a plastic section. Obviously, it is much less than 15.7. Therefore, it will not called a slender section. Therefore, once I am okay that once the section is not slender, even I need to check whether b plus d divided by t, which is 110 divided by 8. Even this is also 13.75. However, as per this, the code says that it should be less than 25 times epsilon. 25 times epsilon means 25. Therefore, it is okay. Means it is not slender. Therefore, it is okay. Hence, once it is okay, then what I'll do is, hence the design compressive strength or compression load or compressive force, all are same. PD is equal to FCD. Whatever that FCD I got is correct, right? Therefore, which is 104.74 multiplied by the area of these two angles back to back is 1634 divided by 10 to the power 3. It works out, say, 171.14 kilonewton, which is just greater than 165.75 kilonewton. Yeah, you please see. Just have just provided the required section. Had you taken the higher section, almost it might have gone up to even 198 or 200 kilonewton, right? If I have just chosen an optimized section, therefore it is okay from compression point of view. However, once it is okay, now what I'll do is I have completed the design for compression. Now I'll check whether these two angles back to back, is it okay for tension. Therefore, hence the next heading is check for tension. However, from class 6.2, page number 32, let me go to that page number 32, student, right, of IS 800, right? Therefore, now I have from this page 32, let me go to that page number 32, right? Yes, I'm having page number 32, right? Yes, design of tension members. Even the other day I have seen how to design the tension members in the same playlist. For elaborate designs, you please go through these videos on the design of tension members, right? Wherein design strength due to yielding of the cross section, TDG is equal to AG Fi divided by gamma m naught, as well as design strength due to rupture of critical section. However, I have to have the angles, right? Therefore, for those angles, right, not single angles but the other sections, in the other section it says that even for double angles, right, the rupture strength TDN of the double angles shall be as per 6.3.3, means akin to that of the single angles. Now TDN is equal to 0.9 ANC Fu divided by gamma m1 plus beta multiplied by AG naught Fi divided by gamma m naught, where beta is equal to 1.4 minus 0.076 W by T Fi divided by Fu multiplied by BS divided by LC. It should be less than or equal to Fu gamma m naught divided by Fi gamma m1. It should be greater than or equal to 0.7. This we already seen the other day elaborately. Even the third criteria is design strength due to the block shear criteria. Using the bolted connections, block shear strength, the TDB is either first one is ABG Fi divided by root 3 gamma m naught plus 0.9 ATN Fu divided by gamma m1, or TDB. Second criteria is 0.9 ABN Fu divided by root 3 gamma m1 plus ATG Fi divided by gamma m naught, right? Therefore, out of these three criteria, whichever is minimum. Therefore, now what we'll do is, now I'll first calculate design tensile strength due to yielding of the cross section. TDG is equal to AG Fi divided by gamma m naught. I'm substituting the numeric value 1634. Fi is 250 divided by 1.1 divided by 10 to the power 3 to convert in terms of kilonewton. It works out, say, 371.36 kilonewton. However, it is just subjected to a tensile factor tensile force of 95.4 kilonewton only, right? Even now I need to calculate due to the second one, due to the rupture of the net cross section. Due to rupture of the net cross section, even the third criteria is due to the block shear criteria. The other day in design of tension members we have explained these elaborately. You may just go through that. However, I'm not going through that because this TDG is almost very large value compared to the top. This 95, almost this is roughly 3.8 times more, roughly 4 times more. Therefore, even assuming just 20 to 30% reduction, even with that assumption also, right, design tensile strength due to rupture and block shear will be approximately either TDN or TDP will be approximately equal to even 20% reduction. If I assume, right, 0.8 multiplied by 371.36, it works out say 297.09 approximately, right, which is much greater than 95. However, this is very vague assumption. For exact calculation, you can go through these codal specifications what you have seen and you can exactly calculate. However, I am not going with the exact calculation because that gross in the gross cross section yielding I am having sufficiently large cushion. Therefore, I hope that these will not fail in the other two criteria, right? However, we already explained elaborately in the previous design of tension members. If you further wish to learn more, then you go through these previous videos on design of tension members, student, right? Therefore, it is also okay in tension. Therefore, it is okay in compression, which is greater than 165.75, and also it is okay in tension. It is also okay in tension, which is greater than 95.4. Therefore, the assumed section is okay. Once it is okay, then I'll go with the bolted connections, right? The bolted connections. Now, already the diameter of the bolt is now assumed as a 20 mm diameter, like this, right? Therefore, from table 19 of page number 73, let me go to that page number 73, student, right? Like this, right? Of IAC attended page number 73, 73, yes, right. Therefore, the connections, once the diameter of the bolt is 20 mm. Now you can see that for standard bolt holes 16 to 22, the diameter of this hole should be 2 mm more. Therefore, that is what I am doing, right? Just adding just 2 mm for getting the diameter of the hole as 22 mm, right? And also from class 10.2.2, page number 73. Let me go to the page number 73 as well as where we'll see the pitch 73, page number 73, right? Therefore, I would have this, the minimum spacing should not be less than 2.5 times the nominal diameter of the bolt. However, we are assuming that the black bolts, ordinary black bolts, even the maximum spacing should not be exceeding 32 times T or 300 mm, whichever is less, right? However, I do have here a compression member. For this compression member, it should be 12 T or 200. However, the T now is also 12 mm, therefore 12 multiplied by 12, 144 or 200, whichever is minimum, right? That is how the pitch. However, let me see what is that pitch. Therefore, pitch should not be less than 2.5 multiplied by 20, 50, and it should not be greater than 12 multiplied by 12, 144 or 200. Therefore, this pitch should not be more than 144. Therefore, I say let us provide a pitch of 50 mm. This pitch, the centimeter distance between the two bolt holes, right? In the application of the load direction. Is called pitch, right? Therefore, even next one is the edge distance from class 10.2.4, page number 74 from the same page. Now I will have the edge distance as 1.5 times the hole diameter in case of the rolled machine flame, cut, sawn or placed edges, right? Therefore, using this, now let me calculate what is the edge distance. This edge distance from the end of the angle, This is what the edge distance, right? You should not less than 1.5 times the diameter of the hole, which is 22 mm. Therefore, 1.5 multiplied by 22 equals to 33. Or say I want to provide the same edge distance as 33. Therefore, even if I go to this class 10.3.3, page number 75, design, let me go to the page number 75. Then I am there in the same page number 75, right? The bearing type bolts. I am using the bearing type bolts, right? When the shear capacity of the bolt VDSB is equal to VNSB divided by gamma NB, where VNSB is equal to nominal shear capacity of the bolts given by FU divided by root 3 NN ANB plus NS ANB. I don't have it here NS ASB. And even I don't require any correction for the packing plate nor other corrections. Even now let me calculate using this formula. Therefore, the design strength of the bolt in double shear. Please see that the bolts are in double shear. The bolts are in double shear because here there is one weak plane, right? Here is right one plane of shear as well as another weak plane, right? Weak plane. Therefore, it is in double shear. Right? Here one plane, another plane, right? Double shear. Hence, that now works out, say 2 double shear multiplied by area of the bolt 245 multiplied by FUB is equal to 400 divided by root 3 divided by 1.25, that whole divided by 10 to the power 3. It works out in double shear for 20 mm 90.52 kilonewton. Now, even if I go to class 10.3.4, page number 75, right? I need to calculate the bearing capacity of the bolt, which is given by VDPB is equal to VNPB divided by gamma NB, where VNPB is equal to 2.5 kb dt FU, where kb is the smaller of 1, P divided by 3D naught, 2, P divided by 3D naught minus 0.25, 3, FUB divided by FU, and 4 is 1, and P is the summation of the thickness of the connected plates, which are the thickness of the gusset plate, which is minimum, right? Therefore, now let me see, right? Therefore, using that kb from the first criteria is equal to E divided by 3D naught, 33 divided by 3 multiplied by 22, say 0.5. The second one is P divided by 3D naught plus 50 divided by 3, 22 minus 0.25. This is also 0.25. Third one is FUB divided by FU, right? 400 divided by 410, which is 0.975. The fourth criteria is 1. Therefore, out of all these, right, 0.5 is the minimum. Therefore, kb is equal to 0.5. Even. Once I get this, now what I'll do is, then what's the thickness? The thickness as per this code is equal to either the thickness of the gusset plate either 12 mm or I am assuming the angles, two angles 8. Therefore, both will act as if 1 unit, 2 multiplied by 8 as if 16 mm. Therefore, 12 or 16. Out of this, 12 mm will fail first in bearing criteria. Bearing is nothing but due to contact. Therefore, in contact, this 12 mm plate, gusset plate, will fail first. Therefore, substituting into the formula, therefore VDPB is equal to 2.5 multiplied by KB is 0.5, and diameter of the bolt 20 multiplied by thickness. Just now we have seen 12, that multiplied by 400 divided by 1.25, that will be 10 to the power 3. It works out at 96 kilonewton. Therefore, the bolt value is equal to the least of these two, either 90.5 or 96. Therefore, 90.5 in double shear will govern the design. Therefore, the number of bolts required to connect this to the gusset plate is either compression or tension, whichever is maximum. However, we have seen that compression force is large compared to that of the tension force. Therefore, I'll recall that as a design force 165 divided by the bolt value. It works out, say 1.83. However, or say let us provide 3 number of bolts. Hence, provide 3 20 mm bolts. Hence, provide 2 ISA 65 by 45 by 8 mm connected by means of 3 bolts in a row using ordinary black bolts as shown in the figure. This is what I am doing, right? Using 3 number of bolts. Now you please see that I am connecting, right? These are the 2 angles I am connecting using 1, 2, 3, 1, 2, 3, 3 number of bolts, right? Continuously, right? That is how the design student. Or even I'll show schematically also like this, right? Let me go back to that schematic, right? As shown in this, right? It's a cross section. If I cut, that looks like this, right? Or in elevation, this top part member, which is the principal compression member, we have designed along with the bolted connection. This is a gusset plate. Which is connected to the gusset plate by means of 3 bolts, right? Now, once I conclude that, now let me see the design of the bottom cord member or the principal type, right? Now, we already analyzed the principal type, student, right? let me initiate the design of principal tie. Therefore, I'm just recalling this design tension force, right? Let me show the design forces, right? Therefore, these are the design forces in this principal tie. Main tie is 148.5 tension and 75.6 is the compression main tie, right? I'll just recall those results here, right? Those results, right? Therefore, there is the design tension 148.5 and the compression force is 75.6, and also it's a length. Let us see the length, right? The length as per this figure, if I see, right, here the length is 2.5, here 2.5, right, whereas in the between these major things it is 6 meter. Therefore, out of this, whichever is maximum, therefore this 6 meter between these two things will govern the design, right? Not this 2.5. Therefore, this length will be governing the design. Therefore, either that or this. Therefore, now I'm recalling both of these, right? Either 2.5 from the left support to the first panel point, from first panel point to the second panel point is 2.5, but from second panel point to the third panel point itself is 6 meter, right? Out of 16 meter, that itself is 6 meter, right? Therefore, that 6 meter will govern the design. Therefore, the length is equal to 6 meter, right? And now what I'll do, even by seeing this, though the compression is just 75.6 and the tension is more, however, generally all these will be governed in compression only, though there is a less compression force, right? Primarily because of the buckling nature of these very small sections will design for compression, then we'll go for the tension, check for the tension. Therefore, now the bottom chord member, this bottom chord member is as shown here, right? Now what I'll do is I'll initiate design for compression assuming two angles placed back to back on a gusset on one side of a gusset plate of 12 mm. Right? Previously the section was like this. Now I'm assuming the section same, just ups and down, right? Like this, right? Or even I'm showing here the section, cross section, right? Like this, right? Now, however, the length is L. The 6 meter is large, too large. Therefore, almost roughly 19 to 20 feet. Therefore, I need to assume a large slenderness ratio, right? Almost compared to that of the previous case, double that I am assuming. Please make a note, student, right? I am assuming not just 100. In the previous case, I assumed 100 because that length was hardly 2.25. However, I would have the length almost 6 meter, almost roughly 2.5 times more. Therefore, slenderness ratio I am assuming 20 from my past experience. Therefore, from the same table 9C, what I have shown already in the previous case, right? Now let me go to that page number 42. Let me revisit to that page number 42, right? Page number 42. Yes, I'm there in the page number 42. Therefore, for Fy is equal to 250 and 200, I do have just FCD is just 36.6 only. If I'm just recalling that value, FCD is equal to 36.6. Therefore, the cross-sectional area required, A is equal to the design compression force 75.6 kN, and that divided by 36.3. It works out say 2083 mm square. However, I already told that increase the area by 25 to 50%. However, I am increasing by 20%. Therefore, 1.2 multiplied by 2083, approximately 2500 mm square, right? But as a student, you increase only by 25%, not less than that one. Otherwise, it may fail because even the span is large. Therefore, if the span is large, even you increase this by 50% more. 50% more, right? If the span is large, if the slenderness ratio is more, then you try to increase by 50% more, right? However, I want to optimize the section, therefore I'm just making a first trial with 20% more. If it fails, obviously I'll increase by say 35%. Later on, I'll go with the 50% more, right? That is how I'll go on changing, right? Therefore, from SP6 for 1967, from the same table what I have shown, right? From page number 102, what I have already shown, right? I'm trying with ISA 100 by 65 by 8, with the longer legs back to back, right? Like this. Therefore, I do have this section student ISA 100 by 65 by 8, for which is furnishing an area of 114 mm square, even Now let me note down that property. Therefore, this area 2514 mm square is just greater than 2500 mm square. It may be okay. To start with, I'm saying okay. Therefore, I'm just noting down what is that radius of gyration about that major axis. That major axis is 31.6, whereas about the minor axis I need to once again interpolate. For ISA 100 by 65 by this one, whereas for 10 mm I do have, right, 27.5, and for 14 mm back to back distance between these two angles, right, 29. However, here the gusset plate is of 12 mm, therefore if I interpolate, what now I get, right? That is for 10, 27.5, for 14, 29, therefore upon interpolation RYY about the vertical axis or minor axis is 29 minus 29 minus 27.5 divided by 4 multiplied by 2, or say 28.25. However, compared to that of this RZZ, this is the less value, therefore this will govern the design. Already told that effective length, because it is bottom chord member is also continuous member, student, already shown, right? Because of that, now I can say, assuming partial fixity LZZ is equal to 0.85 multiplied by L, say, however, L is equal to large value of 6 meter. Therefore, it now works out, say, 5.1 meter or approximately 5100 mm. 5100 mm. Therefore, now that is about the ZZ axis. However, what is that about the other axis, right? It is assuming 1. Therefore, assuming the slenderness ratio about that, because of the discontinuity, LYY is equal to 1 multiplied by L, it is still 1 meter only. Okay? Now, that is how I got LYY as a 6 meter. Therefore, the slenderness ratio about the major axis as lambda Z is equal to LZ divided by RZ, it is equal to 5100 divided by 31.6, because that is 31.6 about that major axis, 161.39. Whereas about the minor axis, slenderness ratio is equal to LY divided by RYY, which is 6000 divided by 28.25. It is 212.38. Compared to that of that major axis, it is more value. Therefore, this still 212.38 is much less than 250 as per this table 3 of IS 800 2007. Just now we have seen in the previous problem. Therefore, it is okay. Once it is okay, if it is not okay, there is no other option but to increase the section from ISA 100 by 65 by 8 to maybe 10 or the higher section as appropriate. Once it is okay, now once again I'll go to the same table 9C, page number 42. Therefore, I do have the slenderness ratio. Though I have assumed lambda is equal to 200, I got 212. Therefore, for lambda is equal to 210, I'll note down that value of FCD is equal to 33.3 from the table, and also for lambda is equal to 220, that FCD is equal to 30.6 from this table. Therefore, that is how 33.3 and 30.6. Therefore, now I'll interpolate. Therefore, upon interpolation, I will get FCD, the design compressive stress. FCD is equal to 33.3 minus 33.3 minus 30.6 divided by 10 multiplied by 2.38. It works out, say, 32.6 is MPa. However, from the table 2, page number 18, or from the figure 19, just now I have shown that B is equal to 68 here, because still this 100 mm is the connected leg and this 65 mm is the outstanding leg. Therefore, outstanding leg is equal to 65, this connected leg D is equal to 100 mm and its thickness is equal to 8 mm. Therefore, this ratio B by T is equal to 65 by 8 is 8.125, is still less than 9.7. Therefore, it is still the plastic, even this is much less than 15.7. Therefore, it is not slender. Even D by T is also 100 by 8 is 12.5. It is greater than 9.7, but it is less than 15.7. Therefore, it is as per this, it is not slender. However, B plus D by T, it is 165 by 8. It is 20.625. It is less than 25. Therefore, okay. Means none of these are giving an indication that the section is a slender section. If it is slender section, then I need to reduce the effective area by that much of ineffective area, right? I'll show that in the next problem, right? Therefore, my FCD is correct. Therefore, design compressive strength and load is equal to PD is equal to FCD multiplied by AE. 32.66 multiplied by 2514 divided by 10 power 3, 82.1 kilonewton, which is just greater than 75.6 kilonewton. Therefore, it is okay. Therefore, my section is an optimized section. Once it is okay in compression, then what now I'll do is that I'll check for the tension. I'll check for the tension. Therefore, just now we have seen that from class 6.2, page number 32, the design tensile strength due to yielding of the cross section TDG is equal to AGFU divided by gamma m naught. 2514 mm square multiplied by 250 divided by 1.1 divided by 10 to the power 3. It gives 571.36 kilonewton, which is much greater than 148.5 kilonewton. Student, please make it out. Even approximately the tensile strength in the rupture as well as block shear criteria TDN and TDB will be approximately, assuming 20% reduction is 0.8 multiplied by 571.36 is around 457 kilonewton, which is much greater than 147. Therefore, I am not going for a check for these actual values. Even if you wish, you can go through the previous video on design of tension members, right, for exact calculation. Therefore, it is okay in tension also. Hence, my section is okay. Assume the trial section itself is okay. Therefore, now I'll proceed with the design of the bolted connections. Assume 20 mm diameter bolt. Just now we have seen that even they are the two angles back to back. Therefore, they are in double shear. Hence, even we obtained the bolt value in the previous subheading as a 90.52. Right. Therefore, that will govern the design. Hence, the number of bolts are required. Out of this tension and compression, you please see that I have to have a tension of 148 as against a compression of 75. Therefore, out of these two, whichever is maximum? 148.5 is maximum, not the compression force. Compression force is only 75. Therefore, 148.5 divided by this bolt value 90.52. I require 1.64. But even here also, I am assuming say 3 number of bolts. Hence, provide two ISA 100 by 65 by 8 connected by means of 3 20 mm dia bolts as shown in this schematic. Student, that is how the schematic, right? ISA 100 by 65 by 8 connected by means of 3 20 mm dia bolts. Now you can see that this is the outstanding leg of 65 and connected leg is 100 mm and the thickness is 8 mm. That of the thickness of the gusset plate is 12 mm, whereas the section is like this. Therefore, this is the bottom chord member right here, right, which is connected by means of 3 number of bolts. 3 number of bolts. Actually, this is a continuous member, student, like this, right? Therefore, it's a continuous member, right? Starting from the left support, right, 2.5 meter, and between these major slings, right? Major slings, right, which is having a 6 meter. Here only the major buckling will happen rather than that of this 2.5 meter. Here, just minor buckling will happen. That is how the design of the bottom chord, which is called the tie, as well as the top chord, which is called the common rafter or the principal compression member. I hope you enjoyed the discussion what we had in today's class, student, right? Therefore, if you have really enjoyed the discussions, right, don't forget to click like, share, subscribe to our YouTube channel. In the next class, we shall see the design of these roof truss, wherein we try to design the struts as well as the main sling, this part, as well as the minor sling, right? Till then, bye bye, students.